And then I will finally come to some implication of the nature of the acoustic source. In fact, many of these finally tie up with the recent DNS studies by Shon. So I'll have one or two slides on that also. And this has been pointed out by the recent review article by Anne Dowling and Haynes. I think Haynes or Haynes is, both the spellings have been used. So anyway, so this all started with looking at the high-speed jet noise when I was with Protapoli and Brent. And so in the case of high-speed jets, I think it has been shown now several times about the Mach wave radiation, and this is a picture from Hortel again. So if one puts a microphone in this field here, the typical signal, again taken by Brent, looks like this. And one clearly sees a spikiness in the signal, which occurs repetitively. So in the classic paper by Ffowcs Williams, he suggested the use of skewness to distinguish such a signal. So since the signal is spiky, we thought it may be possible to extract this information from spectra also. One would think that there is larger intensity in the higher frequency components if you look at it in some normalized fashion. And this is what we did, was to plot this difference spectra versus the Strouhal number. And it turns out that the conditions where Mach wave radiation is supposed to be important, that falls on this solid line, whereas the other conditions where it is not supposed to be important falls on this dotted line. So there's clearly a difference in the nature of the spectra when Mach wave radiation is at least partially dominant. And it turns out that only exception to this is Jack Seiler's data, which was at actually very high convective Mach number, and we think that the reason for that may be the Mach number being, convective Mach number being very high. However, when we looked at this data closely, then something appeared interesting, that all of this data seemed to peak at a Strouhal number of about 0.2. And it turns out this data consists of studies involving hot jets, cold jets, subsonic jets, supersonic jets, ideally expanded jets, non-ideally expanded jets, small jets, large jets, etc. So in spite of the variations in the both measurement facilities as well as conditions, it appeared that there is a peak near Strouhal number of 0.2. And then I thought, since this is again all, whatever I say is limited to the peak radiation angle, then if one can understand why this, if this is so, what is the reason behind this, then one may have the possibility of reducing the noise levels, if we can understand the reason behind this. And in this context, then I went back to many of the studies and tried to see if this can be tied up, in particular with the stability characteristics of the jet. And it turns out that the most interesting information comes out when you look at the data, which includes both spectral characteristics of the far field acoustic signal as well as the flow field. And it turns out that there's very few studies of this kind, and particularly for supersonic jets. And I'm summarizing here these studies mostly by McLaurin's group. And what I have indicated here is the Mach number and the corresponding Reynolds number. So most of the cases, the Reynolds numbers are low, except for this one, which is called as a moderate Reynolds number jet. And what I have indicated also here is from the flow measurement as well as the acoustic measurement, the preferred spectral component of the flow field as well as the acoustic field. And then I have indicated. So it turns out for the 3 supersonic jets here, the low Mach number jets, the preferred peak Strouhal numbers are identical. However, in this case, it was shown by other techniques that the noise was dominated by Mach wave radiation, and these were definitely created by the instability waves on the jet column. However, it is doubtful that these results can be extrapolated to high Reynolds numbers because the directivity pattern of the acoustic field as well as the spectra were not similar to those found in the high Reynolds number jets. However, there was one interesting point that in the case of 1.4 Mach number jet, even though the measured phase speeds were lower than lower than the speed of sound, still Mach wave radiation was dominating. Anyway, this has been discussed in several papers subsequently. I'll just show the spectra for these 3 cases. It turns out the spectra is very narrow band, the acoustic spectra, and it is limited to the peak frequency. Whereas the other 2 cases are interesting in the sense that the moderate Reynolds number, high Mach number case, the directivity pattern as well as the spectra are typical of those found in the high Reynolds number jet, and that holds also for this 0.9 Mach number jet. And this is the conditions which have been used by Freund for his DNS simulations, and from which he has extracted a lot of information about the characterization of the acoustic sources. So in the first 3 cases, here is a comparison of the spectra of the flow field and the acoustic, and one can see that it lies on top of each other. So there's no doubt here in these 3 cases that the Mach wave radiation dominates, and it comes completely from the instabilities in the jet. Now, in the case of the moderate Reynolds number jet, again supersonic, this is the low Reynolds number case where it is peaked, whereas the moderate Reynolds number case is already broadband, and it agrees in shape quite well with very high Reynolds number measurements by at USC. Therefore, this particular jet now has the characteristics of the high Reynolds number jet, even though it's a moderate Reynolds number jet. And it turns out that in this case, the preferred frequency of the flow field is Strouhal number of 0.6, whereas the acoustic is 0.2. So there's quite a difference. Unlike the 3 low Reynolds number cases, in this case there's quite a difference between the 2 preferred frequencies. And this happens to be the case also for the Mach 0.9 jet, which is also the spectra is broadband. There the peak Strouhal number for the flow field is 0.4, whereas it is again acoustic is 0.2. So the 0.2 seems to be, again in these, even all these spectra you can see this dominance of the 0.2. So I cannot say all the spectra have this feature, including measurements of, classic measurements of lush do not fit this picture. But there's a large number of spectra for which the peak Strouhal number seems to be 0.2. Now, in the moderate Reynolds number jet case, the noise is not limited to the Mach wave radiation alone, but there is both contribution from the Mach wave radiation, which is at the higher Strouhal number, and also from the mixing noise, which again peaks. This is the Ffowcs measurements. And again, it peaks, you can see the peak here is at Strouhal number of 0.2. So even when there is mixing noise as well as Mach wave radiation, the overall noise still peaks around 0.2. So this is not a good figure, but these are 3 Reynolds numbers, again Ffowcs measurements, and you can see a peak approximately and the peak is quite rather sharp. So if you are able to reduce this, perhaps there's possibility of, well, again, reducing noise. So now, this is the hot wire measurements by McLaughlin's group in the moderate Reynolds number supersonic jet. And you can see the Strouhal number of 0.6, which starts to dominate initial stages of the jet, and of course afterwards it becomes broadband. But if you look at the microphone signal, it's quite different, even in the near field, not in the far field. So even in the near field, which is only R by D of 8, there's no correlation between the spectra, which is observed from the hot wire measurements, and the microphone. So again, you are starting to get this, the preferred Strouhal number of 0.2 already in this, and I already showed that in the far field, Strouhal number of 0.2 is what dominates. So now the question is, well, this is the hot wire measurements in the Mach 0.9 jet. The preferred frequency here is corresponds to Strouhal number of 0.4. And I wrote to Shon to find out whether he obtained this from his DNA studies, but he said he didn't do this. If it is really important, he will do it, but it requires a lot of work. But he said that it is, what he remembers is approximately 0.4, whereas the acoustic spectra dominates at 0.2, both from his studies as well as the measurements. Now, this is the acoustic spectra for 0.9 jet, and again 0.2 is what stands out. Now, in the case of stability of the jet, one way to check is to excite the jet. This is what McLaughlin's group did. And there was no reason, if you look at the hot wire spectra, the peak Strouhal number was about 0.6. But what was observed was when they excited the jet, the response was very strong at Strouhal number of 0.2 and 0.4, and the Strouhal number of 0.2 is where the far field spectral dominance exists. And in fact, all of their later studies with excitation are restricted to Strouhal number of 0.2. So they obviously found something special about Strouhal number of 0.2 in all their subsequent studies. And it turns out that if you look at the acoustic response of the jet with excitation, there is quite a strong signal at the excitation frequency, because you are inducing instability waves which are excited. Yeah.
One simple question. This Strouhal number is defined with respect to what? With what scales? Is that
jet diameter, the jet velocity, and yeah.
It's not a local Strouhal.
No, not local Strouhal. It's a global Strouhal number. So now I come back, now I go to the studies by Davis, who used a large, initially he started his studies with a small laser beam, trying to correlate the density fluctuations in the jet and the far field, and also near field microphone signals. However, that was not very satisfactory. So what he did was, he used a large aperture sclerin which covered a section of the jet to capture azimuthally coherent structures through this sclerin, dynamic sclerin, and correlated. He found the coherence between the dynamic sclerin signal and both near field microphone signal and far field signal. And it's quite interesting what he found. Again, the coherence was in the near field. The coherence, this is the thickness of the slab of the sclerin system. The coherence was quite high in the near field, very near field. But it died off within about 10 diameters again, the coherence. But the most interesting thing was that when you looked at coherence between the far field acoustic signal and different slabs in the jet at different stations, he found that the coherence was generally very low. In fact, it was not above the noise level. Except when you increase the slab of the jet to cover the whole 7 diameters of the jet, that is up to the potential core, and in the peak radiation angle, the coherence increased to a, well, it was less than 0.1 at under all other conditions except this one. And of course, he suggests whether there is some very large scale instabilities present in the jet, and this needs to be examined. And so what seems to come out of these both studies is that this Strouhal number of 0.2, which I've been trying to hammer on, is definitely tied up with some stability characteristic of the jet from the response studies of McLaughlin's group. And also, it is tied up with the source being an extended source, probably covering a large length of the jet, which comes out from the M.R. Davis studies. And it turns out that Freund, who has analyzed his data, DNS data, in a second paper, in fact shows that if you look at the noise contribution in the far field from different sections of the jet, in fact, if you look at certain sections, the noise field is much higher than the overall noise field, by several dB. So only when you look at the combined effect of the jet, do you get a comparison close to the measured acoustic spectra. So this, I think, I'm coming to the end of it. This is Freund's DNS studies. Again, he finds 0.2, which suits off what I'm saying. But it is DNS studies. This is from, again, the recent review article, which and finally, this is the nature of the sort which is extracted by filtering. That is, you look at the frequency corresponding to this peak Strouhal number of 0.2, and then look at limited wavelength and what the source looks like. It is a growing and decaying instability wave. And the question raised in this review article is whether there is a wave packet which is involved in the far field noise contributing to the Strouhal number of 0.2. I think this is the point which I wanted to bring up. And so, okay, I think, thank you very much.
I'm afraid I might have missed this detail, but is there a variation in the peak radiation direction over all the jets that you showed for which this Strouhal number is speaking at?
Yeah, the peak radiation angle will vary from about 30 degrees to 42 degrees, depends, yeah. It does vary. So we have taken data which, they are not at the same. That is where the lush data is actually at a fixed angle, so it does not show that, same Strouhal number being important.
Professor Arakeri, you made a statement near the end, I'm not sure if I understood. You said that the DNS computations, when you looked at his data, you found that the noise from a limited region was higher than the overall noise?
Yes, that's right. So the overall noise was much lower, in fact, several dB.
Cancellation or something?
Yes, that is what, it's a combined effect of an extended source. So you're looking at, contribution, in some sense, a coherent contribution from a large section of the jet.
Coherence. Okay.
Anyway, this, okay, I think we are running out of time.